So the fundamental theorem of calculus, the first part, that says that if f is continuous on a b, so we have this function little f, then we can create an antiderivative, because if we create this function, we integrate from a up to x little f of t dt, the derivative of that function is f of x. So if we have a continuous function, we can use limits of Riemann sums to create a function whose derivative is little f. And when in the statement of the theorem, we called that guy capital F of x. So what the first part of the fundamental theorem said is that if you have a continuous function, you can create an antiderivative for that function. So you use limits of Riemann sums to create that antiderivative, because the value of the function at any point is determined by taking the limit of Riemann sum. That's the definition of this definite integral. The fundamental theorem of calculus part 2 says basically the opposite. So if f is continuous on a b and capital F is any antiderivative of little f, then you can find the integral from a to b of f of x dx just by taking that antiderivative and evaluating it between the two endpoints. Now this is a shorthand notation. When I have the name of a function and I draw a straight up and down bar with two numbers there, that's shorthand for plug in the top number and plug in the bottom number and subtract the value at the bottom from the value at the top. Okay, so this is saying that if you have a continuous function and you want to find the limit of the Riemann sums between two bounds, all you have to do is find any antiderivative, and you just take the value of the antiderivative at the top bound and minus the value of the antiderivative at the lower bound. So the first part said you can use limits of Riemann sums to create an antiderivative. The second part says you can use any antiderivative to find the limit of the Riemann sums. Now, in order to prove this, let's do this. Let's let g of x be this integral. I'm going to integrate f of t dt here. So we're gonna do this function. Now we know that this is a function whose derivative is f of x. That's what the fundamental theorem part 1 guarantees us. Now if capital F is any other antiderivative, so if capital F is any other antiderivative of little f, then we know from corollary 2 to the mean value theorem that the difference between g of x and capital F of x is just some constant. Now, notice two things. First, that g of b would be the integral from a to b of f of t dt. Okay, and that would be equal to f of b plus some constant. But what would that constant need to be? Well, look at g of a. G of a would be the integral from a to a of f of t dt. Of course, that has to be equal to 0, but also g of a would be f of a plus some constant. So the constant we're looking for is actually g of a minus f of a. So if we put that together here, then we find that since that constant is, g of a is 0, right? So that constant is actually minus f of a. So we find that the integral right here, plugging that in, tells us the integral from a to b of f of t dt is going to be f of b plus c, but we just figured out that that constant was f at a. And so that's what we said that the fundamental theorem part 2 said, right? That if you want to find this limit of Riemann sums. You just take any antiderivative, it doesn't matter which one, and you take the value of the antiderivative at the upper bound minus the value of the antiderivative at the lower bound, and you'll have the definite integral calculated. That's a huge time saver. So here's an example. We have this function sine x from 0 to pi, so we're talking about summing up all of these slices from 0 to pi here, and we want to find what is the value. Well, we could try to set up some kind of Riemann sum, maybe try equally spaced partitions, but it'd be really, really hard to calculate this number using what we know so far. But sine x is continuous on this interval from 0 to pi, and so the fundamental theorem says, well, all you have to do is find an antiderivative of sine. So, well, the antiderivative of sine, an antiderivative, would be minus cosine x. You could think, well, there's lots of antiderivatives, you could add any constant here, but it doesn't matter what constant I add, because that constant will show up in both the top and the bottom. So maybe I could say, well, here's an antiderivative. Doesn't matter which one I use. And I'll evaluate that between the two bounds. So when I do that, I get minus cosine of pi plus 2 minus cosine of 0 plus 2. All I've done is to take my antiderivative. Any antiderivative will do. I just randomly threw in a plus 2 because I knew that derivative of any constant would be 0, and just evaluate it between the two endpoints. Now see, the cosine of pi is negative 1, so we get negative 1, that's 1 plus 2, but then we also get minus, the cosine of 0 is 1. Notice that 2 that I just kind of threw in there cancels because it shows up here, but it also shows up there with a negative sign in front of it. So it really wouldn't matter what constant I threw in there. That constant would show up in both places and it would cancel. So any antiderivative will do. You might as well just use the simplest one that has no constant at all, or set the constant equal to 0 and do that. So anyway, we found that the area under this curve between 0 and pi is actually equal to 2. And it was relatively painless because the fundamental theorem said all you have to do is find an antiderivative. So we did. Let's do another one here. Well, first I have to figure out what an antiderivative is. In order to do that, I'm going to try to simplify if I can. I'm going to multiply this out. Now if I multiply cosine x plus secant x times itself, then I have to use the FOIL method. So I'm going to get cosine x times cosine x, that's going to be cosine squared x, and I'll get cosine x times secant, but actually secant is 1 over cosine, so if you take the cosine times 1 over the cosine, you'll get 1. Then when I take secant times cosine, I get 1 again, and then finally secant times secant will be the secant squared. Okay, now actually have this is pretty good. We've got the integral from 0 to pi thirds of cosine squared x plus 2 plus the secant squared of x. By the fundamental theorem, this is a continuous function, so this is a continuous function, so by the fundamental theorem, all I have to do is to find an antiderivative of this thing. Now I know the antiderivative of secant squared would be the tangent of x, and the antiderivative of 2 would just be 2x. To find the antiderivative of cosine squared is a little bit trickier. I have to use an identity, and the identity I can use is that cosine squared is equal to 1/2 plus 1/2 cosine 2x. This is an identity that you can get from using the angle sum identity for cosine, where the angle is x plus x. So with that identity, now I can find an antiderivative of this. The antiderivative of the 1/2 part will be 1/2 x, and the antiderivative of 1/2 cosine 2x will be, let's see, I know it should be sine 2x. If I take the derivative of that, it kicks out an extra 2, so I'm going to need to be ready with a 1/4 there. Okay, so now I have my antiderivative, so I just have to take the antiderivative, which is 1/2 x plus 1/4 sine 2x plus 2x plus tan x, and evaluate that antiderivative between my two endpoints. If I plug in pi thirds, I get 1/2 of pi thirds plus 1/4 of the sine of 2 pi thirds plus 2 times pi thirds plus the tangent of pi thirds. All that minus the value of the antiderivative at 0. Now, it's 0. If x is 0, we have 0. And the sign of 2 times 0 is a sign of 0, which is also 0. And 2 times 0 here is 0. And the tangent of 0 is 0. So this function was pretty simple when you plug in 0. Let's see what we've got. If we could add all this up, we've got pi sixths, and the sign of 2 pi thirds is the same as the sign of pi thirds, which is root 3 over 2. So we have 1/4 of root 3 over 2. That would be root 3 over 8. And then we have a 2 pi thirds. And then the tangent of pi thirds is root 3 over 2 all over 1/2. So we get just root 3 for that. So to get a common denominator of 8, I'll have to multiply that top and bottom by 8. So this we'll need a common denominator of 6, so I'll have 4 pi over 6. So altogether, I have a pi over 6 and 4 pi over 6 would make 5 pi over 6. And I have root 3 over 8 plus 8 root 3 over 8 makes 9 root 3 over 8. So that must be the value, the limit of the Riemann sums, right, as we add up everything in this function. So notice that in order to find the antiderivative, we had to be a little bit tricky. We had to use some identities. For example, when you multiplied cosine by secant, we had to know you got 1. We also had to know this identity. Anytime you have to find an antiderivative of cosine squared or sine squared, there's an identity like this that works.